Hello. Can you guys hear me? If you can, let me know. Oh. Yep, cool. All right, we'll get started in a few moments. Just make yourselves at home. Sweet, okay. So those of you who are tuning in, if you haven't already, please sign our sheet, or please sign our attendance form. You can scan the QR code, or we can send a link in the chat once I find it. That will help us a lot. Thank you. Okay. So the form should also be in the chat. So yeah, if you haven't already, please sign the attendance form. That would help us a lot. Thank you. All right, so before we get started, I'll kind of give a brief rundown of what the plan for today is. So today we kind of expect about 3 hours of content. The first hour and a half. So it will be uploaded basically after the second half of the stream. All of the videos will be uploaded and you'll be able to find it on the channel. Yeah, so basically the first half will cover pretty much the first half of the course. Mainly we're going over probability theory, going over some expected values, normal distributions, binomial distribution, and then the second half you'll be dealing with things like hypothesis testing, samples, and central limit theorem. So that's the general idea for the stream. This is the first time we've ever done a stream for 1041. So if you guys do enjoy it and find it really helpful, please let us know and we'll be happy to do more in the future. All right. And I'll also be flipping back and forth between the slides and the chat just to make sure that I haven't missed any questions. Yeah. All right, without further ado, let's get started. Let me bring up, okay. So, hello guys, welcome to the MATH1041 revision seminar. This will be a 3-hour long stream split into 2 halves. So the first half, we are going to go over descriptive statistics, probability, and random variables. And in the second half, you'll be dealing with statistical inference, linear regression, and parameters and proportion. So let's get started. So the first chapter is really short just because you won't be assessed on this sort of thing that often. And in fact, I've never really seen a question on this chapter. So it's going to be really brief. It's basically we're going to talk about different types of data. So if you're given a data set, what sort of data set are you going to be provided with? And there are two main ones. So the first one we're going to look at is quantitative data. And all you really need to know with quantitative data is that it really just takes a numerical value, and you can do arithmetic with it. So you can find, say, the mean or the median, or you can find like standard deviation and things like that. So quantitative data are just data points that have numerical meaning to it. So for example, temperature, because you can measure temperature at different points, or the WAM distribution, so you can look at data points of people's WAM. The second type of data is categorical. So if you can't take any numerical values, then the other type of data is called categorical. And all you really need to know with categorical is that you can just basically place these objects into separate categories. And they are basically just used to describe data. For example, color, you can describe color as green, orange, red, blue. So have a whole spectrum of different categories. Or gender, you can have male, female, non-binary, some other ones. But basically, if you can't describe them using numbers, then we categorize them as categorical data. And if you can place a number on it, we call them quantitative data. Yeah. So in saying that, it's good to know that you have these data points and you know what type of data you have, but you then need to do something with that data. So we can summarize categorical variables using what we call a table of frequency. And as the name suggests, really all it is just a frequency table, right? So you have a frequency and a percentage, or the count or proportion. So you measure the percentage of category A and the percentage of category B. You can have multiple categories here. And frequency, it doesn't have to be frequency. It can be like a count, a percentage, a proportion, whatever it is. But basically, it is used to describe how frequent a particular category is to be placed. So if I had, say, for example, if I surveyed 100 people and 50 of them were male and 50 of them were female, then the categories would be male and female. The frequencies would be 50-50, so we count them, and then the percentages would be 50% and 50%. Cool. For quantitative variables, there are two main things that you kind of need to look out for. The first is to describe a quantitative variable numerically, you want to look at the measure of location. And that tells you where particularly, where in particular the cluster of your quantity is. So one way to do this is to look at the mean. And the mean is really just taking the average of your observed values. So in order to find the average, you just add up all of your observed values and then divide by the number of values that you have. So if I had, say, the data points 1, 2, 3, then I add up all of the data points, or 1 plus 2 plus 3, which is 6, and then divide by 3. So the average, or the mean, is just 2. And that's a way to describe sort of where a particular, or where the average of your data points are. And that's a way to measure whether, it's more likely to be at the tail or at the, it's more likely to be at the tail or more likely to be like at the center. And another way to look at quantitative variables is to look at the measure of spread. So how far apart are data points? And in doing that, we can also calculate things like outliers. If there is one particular data point that is really far apart from everyone else, we call them an outlier. And so one way to measure the spread is to look at the interquartile range, which is basically the difference between your third quartile and your first quartile. And that's a way to measure the spread of your data points. If you want to look at a graphical summary of a category variable, so remember that a category variable, you place data points into different categories. Then one way to do that is to use what we call a bar chart. And pretty much this is all you really need to know. You have different types of categories, and then you look at, well, how frequent is category C and how frequent is category A and B as well. And then you basically just measure these in this graph. So it's not too hard, pretty easy to grasp. And the graphical summary of a quantitative variable. So one way to kind of see what how spread and what the location of your data points are, you can look at a histogram. And a histogram is basically using bars to measure different heights. All right, and these heights typically represent the frequency of a particular response time, for example. So in this example, maybe say, I don't know, 3 is the most frequent response time, 3 hours. So we can measure it by a bar. And we can see that there is a lot of cluster around here. So we can see the location is, towards the lower end of the data. And we can see that there is not much spread. It's between 0 and 25. And you can also calculate things like the mean, you can calculate median, you can calculate whether any data points are also outliers. Yep. Cool. So those are the main summaries of one variable data points, and that's really all you really need to know with regards to the descriptive statistics topic. It's not too long, and you don't really need to know a lot about a lot of these. You just need to know the different types of summaries for different types of variables, because if you have a different set of variables or a different set of data points, that controls what sort of graphical thing you need to use or what sort of numerical summary you need to use. Yeah. So we'll go into the bulk of the first half of the course, which is probability, and then we're looking at random occurrence, which is where random variable comes in. Cool. So as with anything, we'll basically introduce some definitions, and then we'll go over some examples. So the first thing to look at whenever you're dealing with probability is an event. And the only thing you need to know about an event is that it's just an individual outcome, right? So say I flip a coin. If I flip a coin, the events are either it's going to land on heads or it's going to land on tails, right? So those are your different types of events. Your sample space then is going to be the set of all possible events from a particular, occurrence. So if we go back to the I flip a coin scenario, then the sample space is either it's going to be a head or it's going to be a tail, right? So those are the only possible events that can happen. And we denote a sample space as an S. And finally, the probability of an event is just denoted by P of A. And that really tells you how likely an event is going to occur. So if we look at a fair coin, so a coin that has even distribution between heads and tails, then we know that the probability of flipping a head is the same as the probability of flipping a tail, right? And so, so that's pretty much what probability is in relation to an event and also sample space. And you'll come to find that the probability of a sample space is equal to 1. And the reason for this is because a sample space covers every possible event. So if we add up the probability of every single event happening, you're always guaranteed to get 1. And that's one of the properties of a probability, which we'll cover in the next slide. So some of the rules that you just have to remember. So this should be pretty straightforward, I think, in the sense of you already know what probability is, maybe intuitively, but this is just a more formal way of layering probability. So the first thing is that any probability or every probability of an event has to lie between 0 and 1. And this should be fairly straightforward. At least it's easy to think about it. You can only get a probability between 0 and 100%. You can't really get a probability of, say, 120% because, well, that doesn't really make sense. So we bound, so the rule is that it's bounded. So it's bounded between 0 and 1. The next thing is covering. So the probability of a sample space is always 1. And again, that comes back to the idea that when you add up the probability of every single event happening, you should always get 1. The additive rule. So this one is a little bit trickier because a lot of people would have seen another version of this, and we'll come to that later on. We'll look at some specific restrictions on what the events A and B are in order for the other rule to occur. But for now, you just have to remember that the probability of either event A or event B happening is the probability of A plus probability of B minus the probability of A and B together. And if you've done things like set theory, then this will come as no surprise. But all you really need to know is that when we calculate the probability of A and then calculate the probability of B, we essentially overcount the probability that they both happen together. So we need to subtract that overcounting factor, and that's the probability of A and B happening. And that will give you the probability of A or B. Yeah. And finally, the complement rule. So if we have an event A, then we define the complement to be A to the power of C. So this is called the complement of A. And the complement rule for probability is that the probability of the complement is just 1 minus the probability of the event. Yep. If you have any questions, feel free to just put it in the chat. I'll be frequently watching the chat, so hopefully your questions won't be missed. Cool. Yeah, so those are the 4 main probability rules that you just have to kind of remember. Hopefully they are pretty straightforward. Nothing too complicated, I think, at this point. Yeah, cool. So again, remember that what I said earlier, maybe you are used to seeing that the probability of A or B is just the sum of the probabilities. And we'll see later on that this is generally not true. We'll actually see a particular restriction on what A and B are in order for this to hold. But for the time being, just accept this fact here, that this is always going to be true, no matter what A and B are, that the probability of A or B is just the sum of the probabilities of A and B minus the probability of the intersection, or A and B together. Cool. Now, we'll look at conditional probability. So before we looked at probability where there was no extra information. But often what you'll find, can we go through this part fast? Okay, yeah, sure. Yeah, so the idea is that for conditional probability, you have some extra information that you're given. So for conditional probability, you're given that an event B has occurred. So what happens is that your sample space has diminished because one part has already occurred. And so what you need to find is the probability of A and B happening together divided by the probability of B. And we say the probability of A given B as, well, we're given P of A slash B is the same thing as probability of A given B. In other words, we know that event B has already occurred. Yeah. So we'll look at an example. So in the survey completed by MATH1041 students, blah, 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 all you really need to know is 60% of respondents were female, 28% of respondents were born in the Northern Hemisphere, 45% of respondents were female and born in the Southern Hemisphere. And we want to show that the percentage of respondents who were male and born in the Northern Hemisphere is 13%. So the way to do this, well, okay, you look at it and you're like, okay, I need to find the probability of male and Northern Hemisphere. So we'll denote the male as M and Northern Hemisphere as N. So we want to find the probability of N and M. So we can use the fact that probability of N or M is the same as this. So that one was our additive rule. And we can rearrange this to get this expression here. So all we did was we added this guy here, subtracted this guy, and we get this. Then what we want to do is we observe that the complement of female and born in the Southern Hemisphere is either male or born in the Northern Hemisphere. So we can write this part here as 1 minus probability of F and S, because remember that the complement of F and S is N or M. And we're given that the probability of female and Southern Hemisphere is 0.45. That's just given to us here. So the probability of N or M is just 0.55. And so we can just substitute everything in. Remember that the probability of male is 1 minus the probability of female. So we end up with 0.13. And so we have proven that the probability of respondents who are male and born in the Northern Hemisphere is indeed 13%. Cool. Okay, so the second part is a conditional probability. So we want to calculate the probability of someone born in the Northern Hemisphere given that they're already male. So the way to do this is, well, okay, we know that it's a conditional probability. So what we want to do is we calculate the probability that both they are born in the Northern Hemisphere and they are male, divided by the probability that they are male. And that is by our definition of conditional probability. Okay, so remember that we calculated the probability of N and M being 0.13. And we know that the probability of male is, well, the complement of the probability of female. So remember that the probability of a female is 0.6. So the complement would be 1 minus 0.6, which is 0.4. And so all you need to do now is just substitute everything into your formula and you get 13 divided by 40. Cool. Okay, so the last part of probability, we will cover independent and mutually exclusive events. And then we'll go back to our additive rule and do some changes to our additive rule. So the first thing is we want to look at independence of events. And all you really need to know with independence is that, well, the probability of A, or A and B, independence means that A does not depend on B and B does not depend on A. So the probability of A is the same as the probability of A given B. So even though B has already occurred, the probabilities don't change. If that is true, then we say that they're independent, and vice versa. And you don't actually need to prove both of them, you just need to prove one of them, and that is sufficient. We also have a second definition that is using the fact that probability of, that should be probability of A given B. So that should be probability of, probability of A given B, remember, is just probability of A and B divided by probability of B. So if substituting this formula in for our conditional probability, we get this second definition here. So it is also sufficient to prove that the probability of A times the probability of B is the same as the probability of A and B. Sometimes it's easier to prove this way, other times it's easier to prove this way. And we'll look at an example. So this is from the 2015 paper. So suppose that you have events A and B, A being the event that the first flip is heads, the event B is both flips have the same outcome, and we want to show that A and B are independent. So using our definition, we need to prove that the probability of A given B is the same as probability of A, or probability of B given A is the same as probability of B. And you can prove either one of them. If you can prove either one, then we say they're independent. So what we're going to do is we're going to prove that, so remember that probability of A and B is the same as probability of A times probability of B given A. That you can easily verify just by looking at the definition of the conditional probability. So remember that if we divide by probability of A, we actually end up with this. So with this formula in mind, well, it's not too hard to show. So the first thing you want to do is, well, I want to calculate the probability of B. And the probability of B is the probability that both flips have the same outcome. Well, if we flip two coins, then we only have four outcomes. We have either heads, 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 tails, tails, heads, or tails, tails. And we know that we want to find the probability that both flips have the same outcome. So it's either heads, heads, or tails, tails. So out of the four outcomes, two of them have the same two of them will have the same outcome. And so the probability of B happening by itself is just half. Now we want to find the probability of both A and B happening. And that only happens if A happens, then the only restriction for B is that the second must be heads, or the second flip must be heads. Because the probability, A happening is your first flip is heads, so the second outcome must also be heads. And so if you want to have the probability of A and B happening, then it's going to be a quarter, because you have heads, heads as the only outcome, and then you have four possible outcomes in your sample space. So we have a quarter as probability of A and B. From here, we know that the probability of B given A is given by, I think I made a mistake here. It should be probability of A, which again is still a half, but yeah, which is probability of B. So this should be probability of A, and probability of A is really just a half. And so we end up with this formula here. And we have this result. We've proven that the probability of B given A is probability of B, and so that is enough to show that it is independent. Cool. And the last thing we want to look at for probability are mutually exclusive events. And these are events where A and B cannot occur together. In other words, they are disjoint. So the probability of A and B happening together must be 0, because, well, mutual exclusive events just means that they cannot occur at the same time. And it doesn't necessarily mean that they're independent, because independent events just means that the events A and B don't depend on each other, whereas mutually exclusive events just means that they cannot occur at the same time. So just be careful that you don't mix those two definitions around. But one of the results with mutually exclusive events is that the probability of A and B is equal to 0. And we'll see that it is only true if A and B are mutually exclusive that this additive result holds. Because remember that the probability of A or B happening is this. So probability of A plus probability of B minus the probability of them happening together. But if they are mutually exclusive, then the probability of A and B is equal to 0. So that means that this section here is 0, and so we get the probability of A plus probability of B. So if you want to show that two events are mutually exclusive, you can either show this result, or you can show that this result here, that the probability of A and B equals to 0. Cool. And that finishes off probability. So some things you just have to remember: independence, mutually exclusive, and then just your basic rules of probability. Well, now for the second half of the first part, or the first half, we'll look at random variables. And this is where you have random occurrences. So we'll look at discrete RVs and then continuous RVs for the next hour. So we'll look at a definition. So for a random variable, we say that something is a random variable when it's a function that takes some outcome from S. Remember that S is a sample space, and you map it to a real number. So you take an event from S, and then you say, okay, well, X of S is equal to some real number. And the reason why it's called random is because it encapsulates a lot of random occurrences that happen within the real world. We'll look at specific examples down here, but the idea is that they basically map very random things that happen in our world. Like if we roll a die, well, there is a random chance of something happening, or the number of people drinking coffee, well, that is also a random variable, or number generated by a random number generator. These are all random phenomenons that we have in the real world, and that's why it's mapped by a random variable. Cool. So the first definition we'll look at is called a discrete random variable. And all you really need to know is that it's a random variable that takes a finite set of values. So we can count each of the outcomes in the sample space, and we can count the events taken by that discrete random variable. So as an example, rolling a die, because there are countably finite set of values that rolling a die can take. The number of people drinking coffee on a particular morning, or the number generated by an RNG. in order to think about this discrete random variable, we need to look at a particular distribution called a probability distribution function. And all you need to know about with this is that it's a function that essentially lists out the likelihood of an event. So if I take x1 to be the event of a 6 being thrown, well, there are 6 faces of a die, so the chances of you rolling a 6 is 1 divided by 6. So we say that the probability distribution of x1 is 1 divided by 6. In the same way, if you have x2 being the event of a head being thrown, then we say that the probability of that happening, of this event happening, is a half. Yeah. Cool. Another thing that you kind of need to know about discrete random variables is the mean. So the mean is essentially, it's sort of like the average, but it's the weighted sum of all of the events. So xi is all of the events, and the probability of that happening. What is an example of a random variable x? So you can think of a random variable as essentially just, an event that happens in real life is, say, the number of natural disasters that happen in the real world, right? It's a variable in the sense that we use variables to describe the phenomena, but it's also random in that it captures the randomness of, say, that event happening, right? So, or an example could be that it's the number of people on a particular bus, right, at any particular time. Well, it's random in the sense that we can't really predict it, but it's also a variable in that we use variables to also map, or to also think about capturing a more generic situation. Hopefully that sort of answers your question. Yeah. So for a mean, essentially all you need to remember is that you multiply the event with the probability. And we'll go through an example of that shortly. So for example, if you have the events being the number of cars, so the random variable is the number of cars owned by a household. So that is an example of a random variable in that it is captured by, it is a random phenomena within the real world, or even, it doesn't even have to be the real world, it can just be, so it's random in the sense that we can't really predict what's going on, but we can sort of make out some properties of this random variable. So as an example, if you have xi being the number of cars owned by a household, then the mean number of cars owned is just, 0 times 0.09, so that should be 0.09, 1 times 0.37, and then 2 times 0.37, and then 3 times 1.7. And then you add them all up, and that should equal to 1.62. So all you really need to do is you multiply the event with the probability and you add them up, and that will give you the mean. Cool. We won't really cover independence in the course just because you don't really need to know a lot about independent random variables, but they work in pretty much the same way as probabilities. Recall that we said that the probability of A times the probability of B is equal to the probability of A and B. Well, that's the same as what you have here. But you don't really need to know the concept. You don't really need to know the full concept of independence. but we'll talk about independence when we talk about things like variance. So one of the rules for expected values is that if you have another random variable, y, being somewhat dependent on what x is, so if y is a linear combination of x with a and b being like numbers, then we can already calculate the expected value of y, because the expected value of ax plus b is the same as a times the expected value of x plus b, which is a times the mean of x plus b. So we'll look at an example. So suppose that you have a random variable x, we want to compute the mean, and then we want to compute the mean of y. So pretty straightforward. The mean of x, you can just read it up here. 0 times 0.4 plus 2 times 0.1 plus 5 times 0.2 plus 9 times 0.3, and that will give you a number 3.9. Then we know that y is 5 plus 9x. So we're using the rule from before. We can calculate the mean of y being, well, 5 plus 9 times the mean, and that will give you 40.1. So you don't need to know anything about the distribution of y. You don't need to know anything about what y is. All you really need to know is that it's a combination of x and some numbers. And then you can calculate the mean, and you'll be able to see that you can also calculate the variance. Cool. So the variance of a discrete random variable is given by this formula here. It's basically just the event minus the mean squared times the probability of that happening. And then you just basically take the sum of all of those numbers. Then you'll be able to find the variance. So it's similar to the mean. The only difference is that this part here changes. So instead of having xi, you have xi minus the mean squared. And standard deviation really is just the square root of the variance. So if you can calculate the variance, you'll be able to calculate the standard deviation. And you'll find that the variance must also be positive or 0, because the standard deviation won't be defined if it's negative. Cool. So as an example, let's calculate the random variable, or the variance of this random variable x. So again, we'll use the example from before. So if x values range from 0 to 9, and we have the probability 0.4, 0.1, 0.2, and 0.3, then we found the mean before being 3.9. So we can find the variance. So it's just 0 minus 3.9 squared times the probability plus 2 minus the mean squared times 0.1 plus 5 minus the mean plus 9 minus the mean squared. And then when you put them all into a calculator, you get 14.49. So this is just basically just bashing into the formula and then putting it into a calculator, and then you'll be able to get a number out, and that will be your variance. So nothing too hard, just following the rules of the formula for the variance, and it comes out pretty nice. Again, if y equals to ax plus b, so if y is a combination of x and some numbers, then we know the variance of y is the variance of ax plus b. But this time, the variance of ax plus b is just a squared times the variance of x. So as long as we know the variance of x, we will also know the variance of y. In the same way that if we know the mean of x, we also know the mean of y. But it also turns out that if x and y are independent, so this is where independence comes in very important. But if we know that x and y are independent, then we know that the variance of the difference between your x and y, well, that's the same as the variance of the sum of x and y, which is just the variance of x plus the variance of y. But you'll see that this is generally not true for any particular random variables x and y. But if they are independent, then this must hold, or this holds. Yep. Cool. So one particular example of a discrete random variable that is very important when it comes to statistics is what we call the binomial distribution. So there are three things that all binomial distributions must satisfy, and they are that an experiment must be repeated n times with each trial being independent. So that's the first thing. So each trial must be independent. The second thing is that they must only have two outcomes, either a success or a failure. If they have more than two outcomes, we cannot categorize this as a binomial distribution. So it's very important that they only have two outcomes. And finally, each of these trials will have the same probability p. If all three of these are met, then we can say that it is a binomial distribution, with x being the random variable of success. So x will tell you the distribution of the success of the experiment. Cool. So the binomial distribution will tell us the probability of an event of a success is given by p of x equals x equal to this. And this here is the binomial coefficient. You don't really need to know much about it. You just need to know how to plug this into your calculator, and that's just the NCR thing on your calculator. Here, n is the number of trials, and x is the number of successes. P is the probability of success. And we can stylize this as x being a binomial distribution with parameters n and p. So here n is the number of trials, p here is the probability of a success. Ooh, so let's have a look at an example of computing binomial distributions. Okay, so we know that a particular coin is biased, meaning that the probability of a head is not necessarily the same as the probability of a tail. And we are given that the probability of a head is 0.9, the probability of a tail is 0.1. Each flip is independent, and the coin is flipped twice. So here, n equals to 2. And we want to find the total number of times the coin shows a head. So if x is the number of heads and we want to compute x equals to 2, we just plug everything into our formula, and that will give us 0.81. So n equals to 2 because it's it's an experiment with two trials. And the probability of a success is 0.9 because x is the total number of times the coin shows a head. So the success of a head is 0.9. And so plugging everything into our binomial distribution, we get 0.81. Cool. Remember that 2 choose 2 is just 1. So that's how we get 0.81. Okay. What happens if we want to find the probability that x is less than 2? So remember that there are only 3 different outcomes that can happen. And the reason for this is you can either flip no heads, 1 head, or 2 heads. You can't flip any more than that because we only have 2 flips. So the sample space then is x equals to 0, x equals to 1, and x equals to 2. And remember that the probability of a sample space is just equal to 1. So that means probability of x equals to 0 plus the probability of x equals to 1 plus the probability of x equals to 2 is equal to 1. And we know that the probability of x being less than 2 is x equals to 0 and x equals to 1. So what we can do here is we can instead write it as the probability of x less than 2 plus the probability that x is equal to 2, and that should equal to 1. So we can move this guy here to the other side, and we get this. Remember that x equals to 2 is something that we've already calculated from the previous slide. So all we need to do is just take the complement, and we get our result. Cool. So the last part of discrete random variables is pretty much you just need to remember them. You don't really need to know you don't really need to know the derivation, you don't need to know how to prove it. You just need to know that the expected value of a binomial distribution is NP, and then the variance is NP times 1 minus P. So that means the standard deviation is just the square root of this. And the last part of the first half, we will cover continuous random variables, but you don't really need to know too much about it. But yeah, let's continue. So a continuous random variable. So remember that when we dealt with discrete random variables, we only dealt with random variables that can only take a finite number of values, right? So you basically can count the number of values that your random variable takes. On the other hand, a continuous random variable will take an interval set of values. So you'll have basically infinitely many set of values that you can take. For example, the time it takes for a bus to arrive, given that you have to measure it with perfect accuracy, right? It's an interval of time, so we call that a continuous random variable. So another example of this is, well, the best example for this is basically just time, because time is always ticking and it's just an interval between the start time and the end time. So as long as you know, as long as you have time, you should always think about, oh, it's a continuous random variable. Ooh. So kind of like before, we looked at a probability distribution, but this time it's a probability density function, and that's just because, well, in order to describe the probability of an event happening, you need to describe it using an area underneath a curve. And if you have done calculus, which you don't go through in this course, you will see that it is actually just an integral, but you don't learn how to calculate integrals in this course. So all you really need to know is that to calculate the probability of a continuous random variable, you find the area under the curve that makes up the event. So it could be, a section of your curve. It could be a section of your probability density function that takes up a particular event. Yeah, and so this is also non-accessible just because, well, you see a lot of these things, but you won't be expected to know how to compute them. But I'm just leaving it here for the sake of completeness. So yes, we can also calculate the mean of a continuous random variable. We can also calculate the variance of a continuous random variable, but you won't be asked how to compute these. Just know that they exist, but you don't need to worry about them. Okay, so we'll look at the rules for the means and the expected values. So pretty much like before, it's the same as the rules from the discrete case. the mean of y, so suppose that y was, say, ax plus b, then the mean of y is just a times the mean of x plus b. And again, the same works for variances. If you have y equals to ax plus b, then the variance of y equals to the variance of ax plus b, which is a squared times the variance of x. And if x and y are independent, then this also holds. So this holds regardless of whether x and y are discrete or continuous. And the last part of this is probably one of the most important sections of continuous random variables. And that's really on this idea of a normal distribution. So you can see that a normal distribution is continuous because, well, it takes up infinitely many set of points, right? And to calculate a particular probability, you calculate just one portion, or you calculate an area underneath this curve. So this is probably the most important thing that you'll ever have to do in, well, at least in the first half of the course, because it pops up quite naturally in statistics. And you'll see a lot of these in the second half of the seminar as well. So very briefly, if a distribution looks like this bell curve or something similar to this bell curve, we can say that it is normally distributed, and we write it using this notation here. So x is a normal distribution with mean mu and standard deviation sigma. There is one very special property in that if mu is equal to 0 and sigma equals to 1, then we say it follows a standard normal distribution, and we use z for standard normal distributions. So we normally use x for non-standard, and we use z for standard normal distributions. Yep. So the only really thing you need to know with this is how to compute standard normal probabilities using R, and how to also find quantiles. So to find the probability, we use p-norm, and p-norm will calculate the left half of the curve. So p-norm 1.6 will calculate z is less than 1.6. But if we want to calculate something like z is greater than 1.6, well, the complement of z is greater than 1.6 is z is less than 1.6. So to calculate p of z is greater than 1.6, we just do 1 minus p of z is less than 1.6, which is the same as 1 minus p norm of 1.6, and you can just put this into R and you'll get this number here. So the probability of z being greater than 1.6 is about 5.5%. For quantiles, we use q-norm. So if we want to find the value c such that probability of z is less than c, then we use q-norm. So if p of z is less than c is equal to this number here, then c is equal to q-norm of this number here, and that comes out to be about minus 1.879326. And if you think about that, that sort of makes sense, right? Because that is going to be somewhere down here. So if we calculate the probability that z is less than it, then, well, it's clearly going to be less than a half. So you can clearly see that the value that you take sort of does make sense. And that's how you can tell that, oh, I'm calculating the right thing. If you calculate it somewhere up here, that might be a little bit concerning because this probability is actually quite small. So that's how you can kind of tell whether what you're actually finding actually does make sense. Cool. The nice thing about a standard normal distribution, well, okay, we'll talk about normal distributions first. So in general, if A is less than B, then we have this property here. So the probability of an interval is P of Z is less than B minus Z is less than A. And you can kind of think about that a little bit. So if, say, A was somewhere here and B was this line here, then we're calculating the region between A and B. So all you need to do is take the probability of Z is less than B, which is this entire region here, minus the entire region that Z is less than A. And that will give us the remaining part, which is the part that we actually wanted to find. Cool. Yeah. So as an example, we'll calculate the probability that Z lies between minus 1.26 and 1.6. And we are given that Z follows a normal distribution. So using this rule, we can break down this probability into two separate probabilities. And from here, we know that the probability that Z is less than 1.6 is just P norm of 1.6. And the probability that Z is less than minus 1.26 is given by P norm of this. And plugging this into R, we are given this number here. So hopefully that sort of makes sense. All you really need to do if you want to find a interval is to break it down into a difference of probabilities, and then we can just plug it into R and then we'll get our answer. Cool. What about if we had a normal standard normal distribution? The good thing about a standard normal distribution is that it is symmetric, about 0. So what that means is that if you calculate Z being less than minus a number, that turns out to be the same as the probability that Z is greater than C. And you can kind of imagine it using a standard normal distribution. So if we go back to this graph here, we can see that if we take one portion here and we say, okay, this is say minus C, we calculate the probability that this is less than, or Z is less than this value here, we get everything here, basically. But this turns out to be the same as this portion here, because of the fact that the standard normal distribution is symmetric about 0. So in doing that, we get this nice result. And so what we can do is we can break up a symmetric interval into something that we can compute using only one thing, using only one P norm value. So as an example, if we wanted to calculate the probability that Z lies between minus 3 and 3, then, and we're given that the P norm of 3 equals to this, then what we can do is we can break up this probability here into two separate probabilities. And from here, we know that from our previous result, the probability that Z is less than minus 3, well, that's the same as the probability that Z is greater than 3. But we know that this is just 1 minus the probability that Z is less than 3. So we can do some algebra and we get to this result here. And remember that P norm of 3 calculates the probability that Z is less than 3. And so plugging everything into our formula, into our result, will give us a really nice number here. So we don't need to know anything about P norm of minus 3. We don't need to know anything else about Z. And we can already calculate an interval here. In particular, if it's symmetric. Yeah. And the last part of this is really just standardizing a normal distribution, which will set you up for the second half of the seminar. So if X follows a normal distribution, but it's not the standard normal distribution, then we can always standardize the normal distribution by subtracting the mean and then dividing by the standard deviation. And if we do that, then we have a new random variable z, which will follow a normal distribution or standard normal distribution. So if we don't know anything about what mu and sigma is, or what mu and sigma are, then what we can do is we can just standardize it. That turns it into a standard normal distribution, and we can do things with it, which we will go through in a bit. So as an example, let's just suppose that X follows this normal distribution. So so the idea is that for a normal distribution, we may not necessarily know that it's a standard normal distribution, because remember that standard normal distributions are something that we want to work with, because standard normal distributions are very nice and have very nice properties that we kind of went through, right? It's symmetric and it has we can do a lot of things with it, more than we can do with just a normal distribution. So if we know that X follows a normal distribution, but it's not necessarily a standard normal distribution, then what we can do is we can standardize it. And in standardizing it, we get a new random variable that follows a standard normal distribution. So in order to do that, we just subtract the mean and then we divide by our standard deviation. And this new result here, we define as z, does indeed follow a normal distribution. That's all you really need to know with regards to standardizing and doing that stuff. All you really need to know is this formula here. And once you do, you know this will always follow a standard normal distribution. Does that explain? If I'm going a bit fast, please let me know, and I will try and slow down. Otherwise, we'll continue. So now we have a normal distribution, X, that is not necessarily a standard normal distribution. So X is not necessarily a standard normal distribution, but we still want to figure out some things about it. So we know that X, or this big X here, is less than the little x here, and we want to find the little x such that it's equal to 0.55. So the reason why we want to standardize this is because with our standard normal distribution table that we get whenever we do statistics, that only covers the standard normal distribution. It doesn't cover anything that may not necessarily be a standard normal distribution, which is always why we want to standardize things. So we can technically just plug this into R and then we can find the value for X, but we will do it in a way that doesn't require us to plug a lot of things into R. The previous question was confusing. Okay. Was it the midterm one? There might be a bit of lag, so there might be a bit of a pause in the stream. But yeah, the previous question was confusing. So I'll try to explain this a little bit again. So the idea is that we have a symmetric bound. So we have this being symmetric, right? It's we have the same values here. So if you want to think about it using your standard normal distribution curve, then we know that it's very symmetric, right? So what we can do is, well, first of all, we know from this result here that we can always break up an interval of values into a difference of two probabilities. So that's what we did. So we started off with this, and then we broke it up into two separate, a difference of two probabilities. Right, okay, so that's the first line. The second line here, we use the fact that Z follows a standard normal distribution. So if Z follows a standard normal distribution, then one of the properties that we can extract is that the probability that Z is less than minus C is the same as the probability of Z being greater than C. So we can replace this result here with the probability that Z is less than 3, is greater than 3. And that's what we did here. So from line 1 to 2, we just replaced this result here with the probability that Z is greater than 3. From lines 2 to 3, there was a lot involved, but I'll try to break it down. So remember that if we go back to one of our probability rules, if we have a complement, so the probability of a complement is 1 minus the probability of the event, right? So if we look at the probability, one of our complement rules, the probability of an event, or of the complement, is 1 minus the probability of the event. So from here, what we can gather is, let me have a look. Well, the complement of Z is greater than 3 is Z being less than 3. So if the complement of Z greater than 3 is Z is less than 3, then what I've really done is I have just replaced it with this here, where C is equal to 3. Yeah. And then from there, what I've done is, well, I just kind of distributed the minus to both terms. And so we get the probability that Z is less than, or 3 in this case, minus 1 plus the probability that Z is less than 3. And we get our final result here. So that's how we get this form here. And from there, well, we know we're given P normal 3 being equal to this, which calculates the probability of Z being less than 3. So if that is the case, then we just replace this with this number here, and we can just plug it into our calculator. Does that make sense now? Let me have a look. If it still doesn't make sense, then please let me know. I will try to fix the slide so it's a little bit more friendly. But yeah, so again, we can standardize a normal distribution. Yep, cool. So we can standardize a normal distribution. And remember that all you really need to know is Z is equal to X minus mu divided by sigma. That will turn it into a normal distribution, or standard normal distribution. And from there, what we want to do now is to calculate, first of all, we want to calculate this result here. So Z is a normal distribution. So we can just calculate Z using Q norm. So Q norm of 0.55 is this number here. And in order to find our value for x, what we can do is we can standardize x so that we get something of this form. So the first thing we want to do is, well, we want to subtract our mean. So remember that this is our mean. So we subtract our mean from both sides. Then we divide by the standard deviation, which is 24.5. And so this here, remember this turns into a standard normal distribution. So we can just replace this with z, and we know that the probability that x is less than x is the same as the probability that z is less than x plus 15.9 divided by 24. So now we want to just basically solve for x. So we set this equal to z, and remember that z is q normal 0.55. So if this is equal to z, then to solve for x, we multiply by 24.5 and subtract 15.9. And that will give us our value for x. And if we plug this into R, we can also see that this is the same as if you were to plug this into R with Q norm of 0.55, comma mean equals to this, and SD equals to this. So you can check that it works. Cool, and that is the end of the first half. I think there will be like a 5 to 10 minute intermission before the second half, the second presenter comes on. So hopefully you guys enjoyed the first half. The second half is more relevant for the finals just because, well, I've seen a lot more questions pop up from the second half than the first half. So hopefully you guys have enjoyed the first half, and hopefully you guys will also enjoy the second half just as much. Otherwise, good luck with your studies. It's going to be okay. Yeah.
Alright, hello. Can I just check if anyone can hear me? So if you can, just let me know in the chat. We'll start in a couple of minutes. Alright, hello everyone. Yeah, so we're getting on to the second part of the course. So I'm Raymond, I'm going to be presenting it. So as Joel said, that the second half is probably going to be more relevant to your exams. There's going to be a lot of questions that you get on hypothesis testing, confidence intervals, that sort of thing. So yeah, just like before, if you have any questions, just put them in the chat. I will be looking at that, and I'll try to answer it as quickly as I can. Okay. So the first thing we will talk about is the idea of a simple random sample. This is important because pretty much everything else later on is going to make some assumptions about how we've collected our data. But the main idea is really that, so if we have a sample of size n, then it should be chosen in a way so that any combination of n has an equal chance of being selected. So all this is really saying is that we don't have any sort of bias in our sampling method. So any observation is equally likely. So in terms of how we can do this the most legitimately, well, that would be if you generate some random numbers and you have each of those random numbers corresponding to some element in the population. And so when you get a number from that generator, you look at the corresponding element in the population, and that's the observation that you collect. Now in this definition over here, we use the word simple. The word simple actually refers to the fact that the sampling is done with no replacement. So the same element can't be observed twice within the same sample. Whereas if we just say random sample without the word simple, so we mean with replacement, then in this case the data actually turns out to be independent and identically distributed. So this is going to be like the main assumption that's actually used later on when we look at, for example, the sample mean and that sort of thing. So we're actually always assuming that the data is independent and identically distributed in order for our assumptions to work. Now, technically, if we have a simple random sample, then they won't actually be independent. But in this course, we're mostly dealing with sample sizes that are very large, and so we can approximately assume this, and there aren't going to be any problems. So just keep in mind that it's important for these observations to be independent and identically distributed. So very briefly, that just means that for independent, it means that what we got for one of the observations does not affect what another observation is. And for them to be identically distributed, well, for example, we're saying each of these observations is normally distributed. So all of them follow exactly the same. Yeah. All right. So first of all, next we're looking at the sample mean and standard deviation. So for example, we collect a sample, we've looked at n, we've got n observations in our sample, and what the sample mean tells us is just sort of like an average. So basically we've added together all of these x1, x2, all the way to xn, so those are our observations. So for example, we're looking at the number of minutes before the next bus arrives. Then in that case, x1 would be the time until, say, the first bus arrives, x2 is the time until the second bus, and so on. So I'm going to add them together and then divide by n. So that's just taking the average. So the sample mean. Now the sample mean itself is also a random variable because it depends on the sample that we have. Like sometimes you might have gotten observations that are a bit larger, sometimes a bit smaller. The sample mean itself varies. But it does turn out that the mean is unbiased, meaning that if you look at the mean of the mean, so on average, this sample mean is going to take the value of mu, which is the population mean. So it means that on average, this mean is going to correctly, okay, so on average, this mean is going to equal to the actual mean of the population. And over here, we've got the standard deviation of the mean. So the standard deviation of the mean is given by sigma here is the standard deviation of the population divided by the square root of n, where n is the number of observations. So if you think about it, that sort of makes sense because if I'm just looking at observations from the population, obviously they're going to be a bit varied. But if I'm taking the mean, it's going to be a bit less varied. So the sample mean always has a smaller standard deviation compared to the population, compared to just taking individual measurements of the population. And these two results can both be derived quite easily from just the definition. using some of the rules with mean and variances. And the second thing here is the sample standard deviation. So, this is like how we can try to estimate what the population is. So on the previous slide here, so this is what the standard deviation of the mean actually is. So it's the population standard deviation divided by square root of n. But the problem is that we might not be able to, well, we probably don't know what this value is, what the standard deviation of the population is. What we can instead is we can try to estimate the standard deviation of the mean using this. So we call this the sample standard deviation. Again, this is a random variable because it depends on the particular sample that we had. So what this really is we're just taking each of the observations and we're looking at its difference from the mean or the sample mean, squaring it and then summing them all up. So summing all of them up, dividing by n minus 1 and then taking the square root. So the sample standard deviation is sort of just an estimate for the standard deviation of the population. Because usually we don't know what sigma here is, we can estimate it using S. Now the standard error is given by S over root n, so that's just exactly the same as this thing we had before, except now we replace the sigma with S. So S is what we're using to approximate sigma. So most commonly in your exam, they're going to ask you to give a population mean confidence interval or confidence interval for something else. So we're going to be looking at different kinds. In one of the example questions a little bit later on, we'll actually try to derive one of them from scratch. So sort of see how it makes sense. But in general, we can say that if x bar, so the sample mean is normally distributed with a mean of mu and standard deviation of sigma on root n, then we can show that the confidence interval is given by this value, by this interval over here. So this is a confidence interval for the population mean. So we're saying the true mean lies somewhere inside this confidence interval with some confidence level C. So for example, like 95%, they're saying that I am 95% confident that the true value of the population mean lies somewhere inside this interval. And of course, this interval is going to lie around the sample mean that we measured. So later on, we'll see how this is derived again. So basically, we've got the sample mean, subtract off this expression over here. All right, oops, let's have a square root on the end. Let's have a square root on the end. So, so it's going to be the sample mean plus or minus a multiple of its standard deviation, and z star here is chosen such that the probability of a standard normal random variable lying within this range from minus z star to positive z star is that confidence interval that we are trying to find. And it turns out that for 95% confidence interval, we want this z star to be 1.96. So our confidence interval is actually 1.96 times of the standard deviation above and below the sample mean. That will give us a 95% interval. Again, I'm watching the chat, so if I'm going too fast, make sure you let me know so I can explain a little bit further. So, okay. So notice that this confidence interval should only be used when the standard deviation of the population is known. So if we know the value of sigma, because otherwise, we'll find that this is not quite a correct. It's not quite correct. So this is the other case where we don't know what the standard deviation is. So this time we use this statistic we call t. So this is actually the same as before. I should have mentioned that earlier. So earlier x bar is normally distributed with mean mu and standard deviation sigma on root n. So earlier from Gerald's slides, you would have learned that we can actually say our test statistic is x bar subtract off the mean divided by its standard deviation, and that would follow a standard normal distribution. That's like the basis for this confidence interval. It's actually exactly the same here. So Why is Z 1.96? Oh, okay. So so the whole idea here is actually, okay, let me see if I can draw. So here we've got this. Okay, never mind, it doesn't work. So basically we have our standard normal distribution. So it looks something like this, and we're basically trying to find an area. This area over here. So saying that the area, the probability that Z lies between Z star and negative Z star, we want this to be 0.95. And someone has done the maths behind it, or you can use your R Studio for this. So it turns out that when this Z star value here is 1.96, then in that case, that area under the curve is going to be corresponding to 0.95. And that's just the idea behind it. So yeah, so 1.96 corresponds to this 95% confidence interval. If we're looking at a confidence interval that has a different percentage, you'll need to be able to interpret the data that they give you. Yeah, but 95% is the most common. So usually you'll see 1.96. And yeah, okay, so over here we have unknown sigma. So here we're using the same thing where our test statistic is the sample mean, subtract off the population mean, but this time we're dividing by S over root n. So again, this is the standard error that we've estimated. This is using the sample standard deviation rather than the population standard deviation like in the previous case. And so, okay, that's good. Okay, so, and basically the idea here is that there's some additional error. Because if you think about it, we can't be so certain. So because here we're not sure what the standard deviation is, we're actually approximating that with the sample standard deviation. So we're actually introducing some additional error here. So if you think about it, for us to create a 95% confidence interval, or really just any other confidence interval, it needs to be larger than the one that we saw previously. We need to make a larger one to account for the additional uncertainty from estimating what the standard deviation is. And basically it turns out that this statistic over here follows a t distribution with n-1 degrees of freedom. So this is no longer normally distributed. So it was only normally distributed in the previous case because we know that x bar follows this normal distribution, but the standard deviation should be sigma on root n. Whereas this time we have used s over root n, and so this expression here is no longer normally distributed. It follows a t distribution with n-1 degrees of freedom. But otherwise, the idea behind constructing the confidence interval is the same. Again, I realized that this should actually have a square root there. I forgot to put that in. There should be s on square root of n there as well. So if I was a t distribution with n-1 degrees of freedom, and just like before, we want to choose t star to be a certain value so that the probability of oh wait, oops, there is another error here. I forgot to fix that. Yeah, so the idea is that if we have something that has a t distribution with n-1 degrees of freedom, then it should lie between negative t star and positive t star with a probability of c. So for example, 95%. And so this t star value you expect is going to be slightly bigger than z star, the one that we had previously. It's going to be slightly bigger than z star because of this additional uncertainty. And so again, you just find it, so in your exam, they should give you the RStudio output for that, and you'll know what that statistic is. The t distribution with n-1 degrees of freedom. So if we have a large value of n, so in other words, if our sample size is sufficiently large, then that's basically saying that the value for s is going to almost exactly be the same as sigma. So if population size is large, then your sample standard deviation is a good approximation for the population standard deviation. And in this case, the confidence interval that you will get is almost exactly the same as the one we got on the previous slide. So if its n is large, so for example 30 or higher, if you want to, you can just use the z values. So for the standard normal rather than for this t distribution. Okay. So next thing we have is hypothesis tests. So the idea here is we want to formally test some sort of claim. So for example, you might think the average mark in MATH1041 is, for example, 75, and you want to test whether that is true or not. Well, maybe you ask some students, you measured the sample mean. It turned out to be, for example, 78. But then you want to figure out, is it really true that the mean is higher than 75? Or is it just because the sample happened to choose people who did better in the exam? So we want to formally test this. And by formally, we actually mean in terms of like probabilities. And so to do this, we need to do a hypothesis test. So to formally test the claim, we need to first set up the null hypothesis, which we say H0, and the alternative hypothesis, which we say HA. So in general, H0 is the statement we are trying to reject, and HA is the statement we are trying to find evidence for. So in the example I was saying just then, I would make my H0, I would make that the, so in that situation, my H0 would be that the mean mark in MATH1041 is 75, and my alternative hypothesis might be, for example, the mean mark is larger than 75. So that's an example. So basically, this is what we are trying to reject in favor of something else. So usually H0, we say that mu is equal to some value mu0. So this is like what we think the mean might have been originally, and now we're trying to say that's wrong in favor of something else. Now, one of the tricky things is that the hypothesis test can be one-sided or two-sided. So one-sided, it means that we're only trying to check if, for example, the mean is higher than 75, or maybe I want to check if the mean is lower than 75. But each time we're only checking one of them. So either just greater or less than. Whereas on the other hand, a two-sided test is just saying, all we're saying is that, so our alternative hypothesis is just that the mean is different from mu0, the one we assumed. It could be larger, it could be less. We're actually looking at either scenario. So one-sided test, we're only trying to check whether it's larger. So in that example just then with the MATH1041 marks, so maybe I'm just checking if the marks are higher. So I'm trying to see whether it's higher than 75. I'm not worried about whether it's lower or not. That'll be a one-sided test. So in order to do a hypothesis test, we need to actually use some sort of test statistic. So it's just something that's meant to give it's something that's going to make us make a decision. So usually we want the test statistic to follow some sort of distribution that we know about very well. And so usually the test statistic is going to be in this form. So it's usually going to be the sample mean subtract off population mean divided by sigma of root n. Because we know that under the null hypothesis, which is x bar has a mean of mu, then this thing here should follow a standard normal distribution. So t should follow a standard normal distribution, as we said earlier. And this actually turns out to be exactly the same as what we said earlier with this confidence interval using the mean. It's exactly the same situation now. Yeah. So again, we can use this test statistic if the population standard deviation is known. So we know this value. And if we don't know this value, then we need to do what we did earlier and replace the sigma with the sample standard deviation S. Okay, so before we do an example, we just need to have this next bit, which is the idea of a p-value. So just then we have this test statistic. So if you think about it, x bar over here is meant to have a mean value of mu. So on average, if I were to do this, if I were to do the sampling and I calculate this value for t, well, t should be quite small because x bar should be approximately the same as mu. So I should expect that t is quite small, and if the mean of x bar is in fact mu. But if instead the mean is actually, for example, much larger than mu, then I would expect that x bar minus mu is going to be quite large, and t is going to be quite large. And so that's basically providing me with some evidence that x bar doesn't have a mean of mu. That's the whole idea here. So if this test statistic here is too large or too small, that's basically telling me that the mean of x bar is not equal to mu. And that's going to give me evidence to reject the null hypothesis. But one of the problems here is what's too big and what's too small. It shouldn't be up to human judgment. It should be in terms of a probability. So that's what the p-value is. So the p-value is the probability that the test statistic takes a value as extreme or more extreme than the observed value under H0. So this is saying that if H0 is indeed true, so as a reminder, H0 statement we're trying to reject. In this situation, usually we're just saying that the mean is a certain value. So we're saying that if the mean of x bar is indeed equal to mu, and I get, for example, a value of t that's equal to 0.5, then the p-value is just saying what is the probability that t takes a value that is 0.5 or more extreme than that. So what is the probability of t being larger than 0.5 or t being less than negative 0.5? That's my p-value. And so if this p-value is very, very small, then that's saying that it's very, very unlikely for us to get such an extreme value of t if the mean of x bar is in fact mu. So, so p-value here is effectively a probability of having more extreme values. But again, still small or large still depends on the situation. Like if my p-value is 0.1, is that high or is that low? Well, we also need to have a significance level. So the significance level is effectively the probability of rejecting the null hypothesis when it is true. So let's just say I have a p-value of 0.01. That would mean that we have a 1% chance of getting a value that's more extreme given the null hypothesis is true. And if we reject it, then that means that for that 1% of the time, we are going to make an incorrect decision by rejecting the null hypothesis. So effective significance level alpha here is actually the probability that we incorrectly reject the null hypothesis in favor of the alternative. So it's really a matter of how sure you want to be. Like quite a lot of times you'll see that maybe we do things at a 5% significance level. So we have less than 5% chance of making an error in rejecting the null hypothesis. So a lot of the time you're trying to be having a level of significance of alpha, and we're saying that if the p-value is less than 0.05, then you might think there's good evidence that we can reject H0. But sometimes if you want to be more accurate, maybe you want to have a value for alpha that is even smaller, like maybe 0.1%. The only problem with that case is that it becomes harder and harder to reject because you need to get more extreme values. Okay, so I think we've gone through a lot of theory, so now let's do an example. So, okay. So the first question here, this one's from one of the past papers. So basically here we have got a gardener trying to determine the pH of the soil. And she wants to check if the soil is less than 6.5, because if it is less than 6.5, then she will need to add some lime to it to make it more, to make it pH higher, so that so it's ideal for her plants. Now she actually carried out 16 samples, and found that the average pH is actually 6.3 with a standard deviation of 0.3. But now she needs to work out, is this actually significant? Is there actually good evidence to suggest the pH is less than 6.5? Or maybe was she just unlucky and chose some samples that just happen to have a lower pH? So how can she be sure that this is representative of the whole garden? So here I want to do a hypothesis test to determine whether the gardener should add lime to the soil. So in order to carry out a hypothesis test, remember the first thing we need to do is actually set up our null and alternative hypothesis. So this time the thing the gardener is trying to prove is that the pH is less than 6.5 and that she needs to add lime. So the thing she's trying to reject is that the pH is 6.5. So we first set up our hypotheses. So our null is that the mean is actually 6.5. Here red and gradient equal to doesn't matter too much. So basically the null is that it's not less than 6.5. And the alternative we're having is that it is less than 6.5. We're trying to prove this, or at least we're trying to find evidence for this, so that she can work out whether she can put lime. So this is a test of the mean. So to test the mean, we will need to have this test statistic. So T here is x bar minus mu over sigma on root n. Let me just check some. Okay. So test statistic is given by this value. I think here I should actually have written S, because this 0.3 here is actually the standard deviation of the sample. So she doesn't actually know what the true standard deviation is. So this should actually be S, it's the sample standard deviation. And so we sub that into our test statistic and we obtain this value of negative 2.67. So under the null hypothesis, T follows a T distribution with 15 degrees of freedom. So if you remember earlier, if we replace sigma with S, then that means that it will follow a T distribution with n minus 1 degrees of freedom. In this case, n is 16. That's the number of samples that she took. So it follows a T distribution with 15 degrees of freedom. And then to find the p-value, so p-value, remember, this is what is the probability of having a more extreme value. So we're looking at the probability that t is even smaller, or that should be greater, less than or equal. So t is as small or even smaller than negative 2.67. And this one was determined from the Australia output. It will be 0.0087. So this is the probability that we get a value that's even smaller than the one we observed. One of the important things to note is that this is a one-sided test. So that means that we're only looking at more extreme values on the negative end. Whereas if this is a two-sided test, so if she's trying to test that H0 is equal to, mu is equal to 6.5, HA is mu is not equal to 6.5, that's a two-sided test. Then you need to look at the probability of observing a more extreme value on both sides. So t less than negative 2.67 or t greater than positive 2.67. In that case, that will be 2 times of this value. In this case, it's a one-sided test, so we just need to have this value. So what this value basically tells us is that there is a 0.87% chance of observing an even more negative value of t if the null hypothesis is true. The null hypothesis is that the mean is 6.5. So if that is true, then there's a 0.87% chance that in 16 samples I'm going to observe the mean being 6.3 or less. That's really just what it means. There's a very, very low chance of that occurring, 0.87%. And so that's saying that there is strong evidence to reject the null hypothesis, and the gardener can conclude that she should add more line. But this is also saying that 0.87% of the time she's actually going to be wrong, and that the pH is actually 6.5, but she's still adding line. So always in statistics, we can't actually prove something. It's just that we have very good evidence for it. In terms of probabilities, only has a 0.87% chance of making a mistake. Okay. So next thing we have is the central limit theorem. So I didn't entirely mention some of the things earlier when we talked about them, but for example, earlier we talked about x bar, and we did all of that stuff for the confidence interval saying that x bar is normally distributed. Well, in fact, x bar is only normally distributed if x itself, so if the random variable itself is normally distributed. But generally that's not true. But the thing about the central limit theorem, this is saying that provided we have x1 to xn being independent and identically distributed, then it doesn't matter what this distribution is, provided our sample size is large enough, we can always say that the mean is approximately normally distributed, with mean of mu and standard deviation sigma on root n. So in other words, it's saying that if we have a large sample size, I can always assume my mean is normally distributed. I don't need to worry about whether x1, x2, and so on follow a, for example, binomial distribution, or whether they're normal distribution or anything else. The mean is going to be normally distributed. Yeah. So in terms of how much is large, usually if you have something like n is 30 or higher, usually that's quite good. But it actually really depends on how skewed your distribution is. But I don't think you need to worry much about that. So everything, of course, you should have n being sufficiently large for you to make this assumption. Okay, so here we have another example. So basically we have a group of 16 women attempting to squeeze into a lift. And we assume that the weights of these women have a mean of 72 with a standard deviation of 8 kilograms. And here trying to compute the probability that the average weight of 16 women is going to be more than 74 kilograms. So for the first part, we note that, the question tells us itself to use the central limit theorem. In reality, this is, I guess, there's going to be some error to this because 16 is not a very large sample size. We can't necessarily be certain that this is going to, we can't guarantee that the normal distribution is going to be a good approximation for this. The question tells us so we can. So we can assume that the sample mean is approximately normally distributed, and its mean is going to be the same as the population mean, which is 72, and its standard deviation is going to be the population standard deviation divided by root of n, which is root of 16. That's what we saw earlier. The mean has a standard deviation of sigma on root n. So we assume that x bar approximately follows a normal distribution with parameters 72 and 2. And the question is asking us what is the probability that the average weight is more than 74. So looking at the probability that x bar is larger than 74. But what we see here is that 74 is exactly one standard deviation above the mean. And the question is telling us here to use this 68, 95, 99.7 rule. So that's saying 68% of data lies within one standard deviation of the mean, 95% of data lies within two standard deviations, and 99.7% lies within 3 standard deviations. So this is exactly one standard deviation. And so 68% of them, 68% of them are going to lie within one standard deviation. But now we're looking at something being one standard deviation away. So 32% is going to lie one standard deviation away from the mean or more. But because we're only looking at being more than 74, so we're only looking at one side. So we're only looking at more than 74, we're not looking at less than, for example, 70. So we're only looking at half of that value, and so that's 16%. So 32% of them lie more than one standard deviation outside of the mean, but we're only looking at the positive end, so being very large, and so we need to divide it by 2, we have 16%. And so another 16% would have a mean that's less than 70. And the other part here is compute the probability that the total weight of the 16 women is more than 1184 kilograms. So I guess it's, well, this is the total weight. So since we're looking at the mean, we look at the distribution of the mean. That's much easier to look at. And it turns out that 1184 is exactly 16 times of 74. So the question of what's the probability the total weight is more than 1184, that's exactly the same as saying what's the probability the average weight is more than 74, which is exactly just what we've done in the previous part. So the answer is again 16%. All right, everyone good so far? Yeah, any questions, make sure you let me know. Okay, so that's the first section. Next section we have over here is the population proportion. So this is basically saying that what is the fraction of, for example, males doing MATH1041. I measure a sample, for example, I look at 10 students, I find that 7 of them are male, so I conclude that it's 70%. Then I want to sort of work out what is the true proportion. So of course, 70% is just my sample proportion. It might not necessarily be reflective of the entire cohort. So, okay, sample proportion. So, over here, x hat. So this is just our estimate of the sample proportion. This is just going to be x divided by n, where x is basically the, okay, so earlier Gerald talked about the a binomially distributed random variable. So x, for example, here is just the number of students. It's the number of males studying 1041 in my sample. So my sample size is n, and p. This is the population proportion. So p is the proportion of males doing 1041. Then in this case, x over here is just the number of males in my sample of n people. And so my estimate of the proportion here, this is really just the number of males in that sample divided by the sample size. So actually very simple. So I'm guessing the proportion, it is just from the fraction of my sample that is a male. So if I measure 10 people and 7 of them are males, then the proportion I estimate is just 0.7. Okay, so it turns out that the mean of this estimate we have above, so the estimate of this one actually has a mean of p. So in other words, we're saying that this is unbiased. So if I were to take these means, then on average, the mean is going to be equal to the true proportion. And over here we have the variance. So it can be shown that the variance is equal to this. You don't need to worry too much about where they got it from, but it can be shown. And so variance is that. So standard deviation is just the square root of this. But just like before, a lot of the time we don't actually know what the value of p is. That is, after all, what we are trying to find. We don't know what p is. So we can only approximate p by p hat. So the value that we, so p hat is the one that is the proportion, the sample proportion, the one in our sample. And so this is approximately that standard error. Okay, so there's another side thing to cover. So we can do the normal approximation. So usually working with binomial random variables is not as nice, especially when the value of n is quite large. It turns out that it's much simpler if we approximate it by a normal distribution. And this again follows from the central limit theorem. If our sample size is sufficiently large, then I can say x, which is anything. X here is, as before, the binomial random variable. It will approximately follow a normal distribution that has the same mean. So the mean of a binomial distribution is n times p, where those are the parameters, and standard deviation the same as the binomial random variables. This is just from the central limit theorem. And here we have p hat, so that's the sample proportion. Remember that is x divided by n. So when I divide x by n, the mean is going to decrease by n, and actually the standard deviation will decrease by root n, or multiplied by root n. No, it will be divided by root n. Well, this is the most important thing here. So this is saying our sample proportion, a sample proportion approximately follows a normal distribution with a mean of p, and standard deviation given by this thing here. So as a rule of thumb, this is a good approximation if the mean and the variance are both greater than or equal to 10. Usually your sample sizes are quite large, so you usually don't need to deal with that. Okay, now continuity correction. So the idea here is that the binomial distribution is discrete. So it can only take integer values like 0, 1, 2, 3, 4, 5, 6. But the normal distribution is continuous. So we need to have some sort of correction to this. Maybe it's better if I can draw a diagram. Okay, so the diagram is not going to look very nice, but we'll do that. Oops. Okay, so basically, oh no, I don't want to do that. So let's just say we're looking at a value, for example, 5. So this is 5. Okay, that doesn't work. Okay, I won't do that then. So, so for example, we're looking at the value of 5. So since x is binomially distributed, there would be a probability mass at 5. Like, for example, probability x is equal to 5 would be, I don't know, like 0.1. But when we approximate this by the normal distribution, this can actually be interpreted as an area. So probability x being 5 is actually an area between 4.5 and 5.5. So at any integer x in the binomial distribution, we can approximate that as the area under the normal density curve from x minus 0.5 to x plus 0.5. So altogether, this area is going to be the same as the binomial distribution at x. So most of the time, this is, I guess, a little bit simpler if you draw a diagram for it. So for example, if we're looking at what is the probability that x is less than 5, then I just want to approximate this by a normal distribution. But I have to be careful here, because x less than 5, that actually means I want x to be 4, I want x to be 3, 2, 1, and so on. And so when I approximate it by the normal, I'm actually saying that this is x is less than or equal to 4. So I'm looking at the probability that x is less than 4.5. Because remember, the mass at 4, so at when x is 4, we actually need to look at the area from 3.5 to 4.5. So if we're looking at the probability that x is less than or equal to 4, then in the normal, this is actually the probability that x is less than 4.5. And instead, if they're asking you what's the probability that x is less than or equal to 5, then we actually need to say that this is x is less than 5.5 for the normal. So the easiest way to think of this is just to draw a diagram, think of it logically. If you try to remember the formula, I think you'll get confused. So this is not including 5, this is including 5. So if not including 5, we're actually just looking at the stuff around 4. So from 3.5 to 4.5. And so we cap it at 4.5. Whereas in this case, we actually look at a case where x equals to 5 as well. And so we need to look at a little bit more. So we need to look at x being less than 5.5. Okay, so next we look at the confidence interval for proportions. This is actually exactly the same as what we did earlier with the mean. So if you understand it once, you've actually done all of these questions. Like, where did this come from? Well, this just comes from the fact that p hat approximately follows a normal distribution with mean of p and standard deviation of this thing on the bottom. And so if I want to construct a confidence interval, this is just like the one before. We just have the sample proportion that we calculate plus or minus a multiple of the standard deviation. And again, this Z star is chosen so that the probability of a standard normal lying within that range is equal to this confidence interval, a confidence level. So for example, if I want to have a 95% confidence interval, again, because this is actually a normal distribution, I'll be taking Z star equal to 1.96. So I'm looking at 1.96 standard deviations above and below the sample mean value that I obtained. That will give me a 95% confidence interval. You'll notice here that again we have actually approximated p with p hat. Okay, so now we have an example. So trying to calculate the, well, first of all, they want us to derive the 95% confidence interval, given that p hat is normally distributed with these parameters. So, so we're proving it for this case, but this is actually exactly how the other confidence intervals are derived as well. So all of them follow exactly the same method. Okay, so we know that p hat follows that distribution. And so it follows that if I subtract off p and I divide by the standard deviation, then this would follow a standard normal distribution. That was as Gerald covered in the slides. So if we subtract off the mean, divide by standard deviation, we get a standard normal distribution. And so if I want to construct a 95% confidence interval, then because this is a standard normal distribution, I want this to lie between the 2.5 and the 97.5 percentiles of the standard normal distribution. So it turns out that those values are negative 1.96 and 1.96. So we're saying that if this expression here lies between, we're saying that if this thing here is normally distributed, it will lie between negative 1.96 and positive 1.96 with a 90% probability. Or equivalently, we're saying that there is a 2.5% chance of it being larger than 1.96 and a 2.5% chance of it being less than negative 1.96. So those are the 2.5 and the 97.5 percentiles. And so we're going to derive the confidence interval. That's actually just by rearranging this equation. So I just need to multiply this thing on the bottom, multiply it on both sides, and then basically I move the p hat out, like I subtract it from all sides, take the negative, and I will end up getting this expression on the bottom. And again, I have just approximated the p with p hat over here, so that we can estimate what the standard deviation is. And the second part is to actually construct the confidence interval. Well, just from this particular question, all I need to do is sub it into this thing I've already got. And I just need to make use of the fact, so all I need to find here is what is p hat. The p hat is our sample proportion. As I said here, as I said earlier, that really is just the fraction of like positive results. So here we're really looking at 466, that's like how many were actually diagnosed, divided by my sample size of 6272. So that's my sample proportion. So sample proportion, I get this value, and n is my number of samples, that's 6272. Now if I just sub in these two values into that expression, I will get P is between 0.0678 and 0.808. Okay, I think I'm missing a 0 there. Yeah, it's almost certainly a 0 there. It's 0.0808. Okay. Now next off we have hypothesis tests for proportions. So again, it's very, very similar to what we did earlier. It's just with sample proportions instead of mean. So again, a null hypothesis, that's the thing that we're trying to reject. So P is equal to some certain proportion that we might believe, and our alternative hypothesis is just to prove it's something else. Like maybe we think it's larger, maybe we think it's less than, or just not equal to P0. So we want to provide some evidence to reject H0. So in this case, Z here is our test statistic, as we covered on the last slide. We choose this to be our test statistic because it follows a standard normal distribution under the null hypothesis. So in terms of how do we conduct these hypothesis tests, well, in exactly the same way as before. And remember, we can have one-sided tests and two-sided tests. Okay, so this is a question from a past paper. So basically, okay, rest of the stuff are basically they were asking people for whether they prefer Labour or Liberal, and it turned out that the proportion preferring Labour was 0.51. So the sample size was 100, and we want to construct a 95% confidence interval for the proportion preferring Labour. So basically what they might be trying to do here is they're trying to check if, with 95% confidence, if the proportion of people that vote for Labour is going to be 0.5, for example. Because even though here they get 0.51, well, the sample size is only 100. They want to work out whether this value here is actually significant. So, here is some RStudio output. We will find that useful a little bit later on. Okay, so first of all, the expected proportion, or I should say this is the sample proportion. That's just 0.51. That's what they found from the sample. So they're actually just saying, well, the sample size is actually 100. So basically, they sampled 100 people, 51 of them voted for Labour, 49 of them voted for Liberal. So the sample proportion we have is 0.51. And the standard error we have is, again, given by this expression that we've shown on the previous slides. That turns out to be 0.05. And to construct a 95% confidence interval, so the expression we had earlier, we're trying to look at p hat minus z star times standard deviation, p hat plus z star times standard deviation, where z star is chosen so that a standard normal random variable lies between negative z star and positive z star, with probability equal to the confidence level, which in this case is 95%. Now, what the RStudio output here tells us is that, well, they tell you all of these things, but the only one here we actually need is this one. So this is 0.975 percentile, or I should say, yeah, so this is 97.5th percentile. So this is saying that 2.5% of, okay, so if something follows a standard normal distribution, then 2.5% of them are going to take a value that is 1.96 or higher. And because we know that the standard normal is symmetric about 0, it means that there is also 2.5% that is less than negative 1.96. And so altogether, we're saying that 95% of the data is going to lie between negative 1.96 and positive 1.96. And because we're constructing a 95% interval, this is the one we use. If it was asking for a 90% interval, I will be using this one. If it was asking for a 85% confidence interval, then I will be using this one, because it's on both sides. That's very important to note. This is 2.5% on one side. We also need to have 2.5% on the negative side. So overall, okay, where did I get this? I just subbed it straight into that equation. So this is the sample proportion, subtract off the z star, multiplied by the standard deviation. This one is minus, this one is plus, and this is our confidence interval. Okay, that was that section. And the next section we have is going to be on the parameter tests. Oh, sorry, the two parameter tests. And first of all, we have the two sample t test. So this is when we have two samples and we want to investigate whether the population means are the same. So again, we're trying to investigate whether there is a relationship. Our null hypothesis suggests that there is the means are the same, and alternative is going to be, for example, the means are different, or maybe I think one of the means is larger than the other. So I'm trying to so basically here we're trying to show the means are different. Okay, and so the test statistic we use here is given by this expression. If you want to, you can just memorize it. But actually this makes a lot of sense. Because if we assume that x1 and x2, well, x1 bar and x2 bar, if they are both normally distributed with the same mean, then that means that the difference between them is going to have a mean of 0. And the standard deviation of this difference is going to be the sum of the, it's approximately the sum of, it turns out the variance of this difference is going to be the same as the variance of, it's going to be the sum of the variances of each of them. And so this expression here is actually just this thing here, subtract off its mean, which is 0, divided by its standard deviation. And the standard deviation is given by this value. This is really just the two standard deviations added together, but they are weighted. They are weighted because one of the sample has size of n1, one of them has a size of n2, so one of them is more important than the other in terms of the standard deviation. So that's actually all this is. Subtract the mean divided by standard deviation as usual. But again, we're actually approximating the standard deviation with like the sample standard deviation. And so instead of following a normal distribution, this actually follows a t-distribution with n1 plus n2 minus 2 degrees of freedom. But as we said before, if the degrees of freedom is sufficiently large, we can just approximate this with the normal distribution. Okay, so this test here actually does assume that they have the same standard deviation and are normally distributed. Now, we know normally distributed, this doesn't really matter because if our sample size is large enough, then x1 bar and x2 bar are going to be normally distributed by the central limit theorem. Having the same standard deviation is a little bit problematic. There are ways that you can deal with it, but we don't really deal with it so much here. So don't worry too much. Okay, so confidence interval, this is exactly the same as the other confidence intervals we've had before. So it's just the sample difference. Okay, so basically I have a confidence interval for the difference in the means, and this is going to be approximately the same as the difference in the sample means. But to get this confidence interval, we're going to plus or minus some multiple of this pooled standard deviation, right? So this thing over here, that's the standard deviation, and multiply it by some value t star, where again it's chosen so that we get the confidence. So the probability of it lying within this interval is the level C that we actually want. Okay. The other test we have is the paired t-test. So this is if we want to investigate whether there is a difference in mean in two samples when they are paired with each other. So for example, I have got some, I've got like for example 10 dogs, and I want to track if they have grown bigger in 2 years. I'll be doing a paired t-test. So here is different from the previous one because the samples are not independent. We actually have pairs of data. We're comparing, like for example, before and after. So we actually need to use this paired t-test. So the null hypothesis we're going to have here is that there's no difference. Both of the samples that I've taken have a mean of 0. So x1 and x2, if I subtract them, it's going to be 0. Now my test statistic here is going to be d bar. So basically di is the difference in the ith pair of observation. So for example, I have 10 dogs, then d2 would be, for my second dog, what's the difference in its size in the 2 years? And this is d bar. So I'm just taking the sample mean of those differences. So mean of those differences. And I divide it by SD on root n. So SD is just a standard deviation divided by root n because we're looking at the mean. So the standard deviation of the mean, it needs to be divided by root n. This is again the same form as the other test statistics we looked at. So it's test statistic, subtract off the mean, divided by the standard deviation. And again, the mean is 0, so we just didn't write it there. So this follows a t-distribution with n-1 degrees of freedom. Again, because we're approximating s, we don't actually know what it is. Okay. Now the next test we have is the chi-squared test, or test of independence. So this is saying I want to determine whether two random variables are independent. So very briefly, what does it mean to be independent? Well, if x and y are independent, what I'm saying is that if I know what x is, it doesn't tell me anything about what y is. Or if I know anything about y, it doesn't tell me anything about x. In that case, they're independent. So again, we're trying to prove for dependence. So null hypothesis, we're going to make that the two variables are independent, and HA is going to be the two variables are not independent. So this test is a little bit more confusing if you haven't really seen it too much before. So in order to do this, we need to first construct a two-way table. One of those is going to be on the next page, so something like this. So for example, I'm having gender versus employment area. This is saying I've got 33 people who are female and are doing commerce, etc. That's a two-way table. And under the null hypothesis, the expected count under H0 is given by row total times the column total divided by n. We'll see this with the example very soon, but this actually makes quite a bit of sense. Okay, so the chi-squared test, and so we know the test statistic is actually given by this. This is a bit more complicated. You don't need to worry about why this is the case. You can just accept it. So if I do the observed count, this is, for example, I have 33 females in commerce. That's the expected. That's the observed count. The expected count is the value that you calculate from this formula. So we'll do an example of that. We subtract it, we square it, and divide it by the expected count, and then we sum that up. So I'm going to do that for each of these 6 and then add them together. And that's my x squared observed. And it follows that under the null hypothesis, which again is that the two variables are independent. So under the null hypothesis, it turns out that x squared over here actually follows a chi-squared distribution with r-1, c-1 degrees of freedom, where r-1 and c-1 are, okay, well, r and c are simply the number of rows and number of columns in the table. So So some of the assumptions here that we've made is actually the sample size is always large enough that the expected count should always be greater than 10. Otherwise, this is not going to be very accurate. And other thing to note is that this is always a one-sided test. If you think about it, earlier we were trying to see if our sample mean was like too large or too small. So there were two different sides. But here we're actually looking at the squared difference between the observed count and the expected count. So having a very small value of x squared is just saying that our observed count is pretty much the same as expected count. Pretty much they're independent. So all we're looking at is actually extreme values on one side. We're looking at whether x squared here is very large. If it's very large, we have good evidence to say that the two variables are not independent. So it's always a one-sided test. So if you're calculating p-values, you don't need to multiply by 2. Okay, so here is the example that we're going to do. So here they had a sample of 400 people, and they looked at the gender and the employment area. So carry out a test of whether employment area and gender are independent or not. And they gave us the observed x squared value to make it easier. Okay, so the first part of the question is to clearly state the null and alternative hypotheses. So for chi-squared test, this is always the same. Null hypothesis is that the employment area and gender are independent, and the alternative hypothesis is that they are not independent. And so next up, the second part of the question actually is this. So under the null hypothesis, verify that the expected count of respondents that are employed is 117. So basically they just want us to do it for female in service. So 137 here is the observed value. So in their sample of 400 people, they found that 137 of them are female in service, and they want us to calculate what the expected count is. So if you want to, you can just memorize this formula. It's the row total times the column total divided by n. So row total is 137 plus 58. Column total is 240. So I do 240 times 195 divided by the sample size, which is 400, and I get 117. The other way to think of it, which is like more intuitive, is that under the null hypothesis, we're saying that gender and employment area are independent. And so it's saying that it's equally likely for a female to be working in service as it is for a male to be working in service. But the idea is that we actually surveyed 240 females and 160 males. So in total, we have something like 195 of them doing service. And so if it was truly independent, then the number of females in service should be 1.5 times of the males in service. That's simply because we surveyed 1.5 times as many females as males. That's the sort of idea. So I've got 195 of them. I should expect exactly 3/5 to be female, 2/5 to be male, because this is 3/5 of 400. Or similarly, to calculate the expected count for female in industry, that should be 2/5. No, that should be 3/5 of 117. So it should be equally likely to be female or male. So each of these values should be in the ratio of like 3 to 2. That will be the expected count. So that's exactly what this formula actually does. So we're doing row total times the column total divided by n. And here we get 117. So it's saying that if they were indeed independent, this one here should be 117. And basically you would do that with each of the other ones. So just then we just did it for this one. And the next part is to show the contribution to x squared from the table entry corresponding to surface and female. So what do we mean by contribution to x squared? Well, going back, we're actually referring to this thing. This is x squared, our test statistic. So for each of these boxes, we are contributing this. The observed count subtracting the expected count squared divided by the expected count. That's the contribution. So the observed count of female in surface is 137. The observed count of, the expected count we saw is 117. And so the contribution to x squared is, sub it in, 3.42. And so in order to calculate what this statistic actually is, you would need to do exactly the same thing for all 6 of these and then add them up. When you add them up, you would get the statistic. But of course, you're doing the same thing many times. It's a bit tedious, so the question is actually giving us the answer. Now, part D is state the distribution that can be used to assess the significance of x2, of x squared, our test statistic, given that h0 is true. Now, on this slide earlier, we said that under h0, so if they're independent, then x squared follows a chi-squared distribution with r minus 1, c minus 1 degrees of freedom, where r and c are the rows and columns. So in this case, we have 2 columns, 3 rows, so the degrees of freedom should be given by 3 minus 1, 2 minus 1, and we get 2. So it's saying that x squared follows a chi-squared distribution with 2 degrees of freedom, because this will allow us to calculate the p-value. So the value that they actually observed is 27.11. So p-value, reminder, is the probability that we get a value that's as extreme or more extreme. And because this is a one-sided test, we're only looking at the probability that x squared is larger than this value we got, which is 27.11. And in that year, they had some data tables in their exam, and you would be able to see that it's actually less than 0.005. So what they're saying is that if they are indeed independent, there is less than 0.5% chance of us actually observing something like this. And so in other words, that is very strong evidence that these are not independent. And if you look at the data, that sort of seems to make sense, especially for something like commas. You'll see here that even though females are 1.5 times the number of males, they've actually got quite a few less. But this is more formal. This tells us in terms of a probability, there is less than 0.5%. And so finally, state your conclusion in terms of the hypotheses. So since the p-value here is very small, we have strong evidence against the null hypothesis and in favor of the alternative. So in other words, we're saying, or we have good evidence for saying that they are actually dependent. So that's saying that if I know something about someone's gender, then I have more information about where they're employed. Or if I know where someone is employed, I actually have more information about their gender. Okay. Everyone good so far? Okay. All right, so last section we have is on linear regression. So first we'll talk about the least squares regression line. So this is just finding the line that minimizes the sum of squares of the residuals. So what that really means is that we want the line so that if I look at the y value at a point, or if I look at all the data point and I look at the vertical distances from this line and I square them and add them together, that's the sum of squares. I want to minimize that. And if I minimize that, then the line that minimizes it is the least squares regression line. So generally our least squares regression line is of this form. So B0 is our intercept and B1 is our slope. So it turns out that the best estimates of the slope and intercept are given by these things over here. So first of all, I can find the slope by taking the ratio of the sample standard deviations and multiplying by the Pearson coefficient. And the intercept can be found by having y bar minus, I should say b1 x bar. I forgot to fix that. Okay. Yeah, that should say b1 multiplied by x bar. So the sample mean for x. And overall, our line can be written as y is equal to, our data can be represented as y is equal to y hat plus the residual. So this is the data we actually observe. This is saying that we think it follows some line, but there's also going to be some sort of residual, which is generally normally distributed with constant variance. So the data is randomly going to appear slightly above or below the line. But the values that are represented by my line are basically the mean values. On average, it will take these values. But not quite, because again, these are sample slopes and sample intercepts. It depends on the particular sample I got. Sometimes it will be a little bit different depending on the sample. And so then we look at the population regression line. So this is, you can think of this as like the true regression line. So the population regression line is denoted by this. Usually we use the symbol mu y. So we're saying that for a given value of x, this is the mean value for y. So beta 0 here is again the intercept, beta 1 is the slope. The difference between this and the previous slide is that these are themselves random variables. They are changing. Whereas here, beta 0 and beta 1 are not changing. They're fixed. It's just that we cannot observe them. We can only approximate them with b0 and b1. And so here we say that y is equal to mu y plus some sort of error. And the error term is again normally distributed with zero mean and the same variance at each x value. So for inference of the slope beta 1, test statistic again is in exactly the same form as before. We have it subtract off the mean divided by a standard error. Because we don't know what the standard deviation is, we're only estimating it. This follows a t distribution of n minus 2 degrees of freedom. And we can get a confidence interval by having our estimate, and then we subtract or we add some multiple of that standard error. So here you don't need to know how the standard error is calculated. If it comes out in your exam, they will give it to you. And t here is again just the value, so that's the area under that t distribution between negative t star and positive t star is equal to the confidence level C. And so generally what we can do is test for whether there is a relationship between the variables x and y by using the null hypothesis beta 1 is 0. Because beta 1 equals 0 is effectively saying that mu y is equal to beta 0. So we're saying that the mean y value is fixed no matter what x is. Or in other words, they're not dependent on each other. There's no relationship. Okay, so in your exam, you're probably going to get a lot of questions on analyzing residuals. So residual, remember, this is actually just taking the difference between the observed y value and the y value that we get from the regression line. Because obviously the data points are not going to exactly lie on the line. So it's important to recognize some of the assumptions that we've made in fitting the regression line. The errors should be normally distributed with zero mean and constant variance. So this means that if I plot the residuals against x, there should not be a pattern. What that means is that I should be getting something like this graph here on the right. The mean is 0. There is zero mean. And we can see that the variance approximately is the same no matter what x is. that are equally dispersed, whether it's when the study is equal to 0 or when study is equal to 8. So there is no pattern. If there is some pattern, then that tells us that there is some poor fit. Like maybe there is additional relationships between them that we have not yet accounted for with just the line. So perhaps they don't have a linear relationship. Maybe they have like a some sort of other curve. One other thing you can do is to plot the residual quantiles against the quantiles of the normal distribution. If they are normally distributed, we should get a 45-degree line. That's when like you plot them on the same scale. So like the quantiles should exactly match up, because we said that the errors are normally distributed. So the quantiles should match. It should be a 45-degree line. Okay. So this is the last example we have over here. So basically they interviewed 64 university students, and they tried to see if the hours of sleep had an effect they actually want to see if the hours of study had an effect on the hours of sleep. And this is the data that they provided. So as study changes, it turns out that their sleep also changes. And they've given us the asked to do their output. So we've got the intercept, and the study here is actually just the slope. Is the relationship between sleep and study statistically significant? So is there a relationship? Well, all that is really saying is we're actually just looking at the slope. Can we be certain that this slope here is different from 0? Or at least do we have good evidence that this slope is different from 0? Now, if you look at it, so this data is saying that so we're concerned with the study. That's the slope. So the slope is negative 0.30. So that's saying that for every additional hour of study, they sleep for 0.3 of an hour less. Now the standard error is 0.0884, and what they have here is a t-value. This is actually under the null hypothesis that there is no relationship. And they've actually given you here the probability is greater than the absolute value of t. That's the p-value for a two-sided test. So this is saying that the probability of getting a more extreme slope, so either less than negative 0.3 or greater than positive 0.3, is actually 0.09%. In other words, almost impossible, very, very unlikely. And so our answer to this question is that there is statistical evidence to support that there is a clear relationship between the study and sleep. That's what this p-value here tells us. Okay, write down the linear regression line equation for predicting sleep from study. So all we need to do is have the intercept, that's 7.7, our slope is negative 0.3, put that in, our sleep is just equal to the intercept plus the slope multiplied by the study plus the residual. And part C is estimate the mean sleep if study is 6 hours. Well, all we need to do here is just sub in study is equal to 6. The residual is normally distributed with a mean of 0, so I can just treat that as 0. So I do this value minus this one times 6, and we get this value. So if someone studies 6 hours a day, then they only get around 6 hours of sleep. And finally, the D is estimate the change in the mean sleep for a 1 hour increase in study. So if someone studies for an additional hour, what's the mean and what's the sleep that decreases on average? Well, that's simply what the slope is. So when study increases by 1, the y value decreases by 0.3. That's exactly what the slope means, and that's the answer. So someone who studies an additional hour sleeps less by 0.3. Okay, and that's so we've reached the end of the slides. So does anyone have any questions? Otherwise, good luck to everyone for your exams. Hope you learned something from today's seminars. Hope you enjoyed it. And as you said, if you enjoyed it, just let us know so we can keep holding these in the future for other 1041 students.